My name is Hasan, Associated Professor, Karadeniz Technical University, Department of Mechanical Engineering, Construction and Manufacturing Department. My topic is Tribological properties of molybdenum disulfide particles as lubricant additive on the performance of statically loaded radial journal bearings. Journal bearings have a great effect on reducing power losses in mechanical systems. One of the most important working issues of recent years is to reduce friction even more with the addition of inorganic compounds as additives to the engine oils used between the relative movement shafts and bearings. In this study, the effect of additive engine oils on bearing performance were investigated by adding 1% by weight molybdenum disulfide to the base oil Shelterless 10. As a result of the experiments, it has been observed that the molybdenum disulfide added engine oil exhibits less friction behavior than that of base oil, increasing bearing load and temperatures, resulting in less wear and power loss by forming a better oil film. Lubricants play an important role in decreasing friction and wear of mechanical contacts. To reduce maintenance period and power loss of rotary machine, some of additive oils have been added to base mineral oil in various industries. Additives have been used to improve lubricant oil properties. These include anti-wear additives, extreme pressure additives, viscosity control additives, film forming additives, and deposit control additives. A good lubricant should have a high viscosity index, high flash point, and low power point. Non-additive oil-based lubricant exhibits extended lubrication performance of tribological applications. The result revealed that pure oil containing 0.5 weight % nano-additives could strikingly improve the tribological properties. Numerous studies have been conducted that to investigate the tribological features of molybdenum disulfide nano-additive oil-based lubricant. The results proved that the lubricity characteristic of the prepared nanofluid is strikingly improved with the incorporation of molybdenum disulfide nanoparticles. In journal bearing tribology, their lubrication regimes are often defined boundary, mixed, and full film lubrication. These lubrication regimes can be explained by this feedback diagram as shown in figure 1. This section is boundary lubrication, second section is mixed lubrication, fourth section is full film lubrication. In these experimentally working sections, this study elementally compares the effect of molybdenum disulfide on the base engine oil Shelterless 10 in the statically loaded radial journal bearing. Furthermore, the impact of the particles of molybdenum disulfide concentration on the tribological behavior of lubricants is explored. To determine the friction behavior, the bearing systems has been modified and constructed. The structure of the particles were characterized by scanning electron microscopy. Material and methods. To investigate the effect of additive engine oil on bearing performance, a journal bearing test rig modified specially for these researches. Typical physical characteristic of the base oil Shelterless 10 shown in Table 1. Tests carried out two different oil temperature. Each test oil temperature remained in the range of 25 and 30 degrees centigrade and 50 and 60 degrees centigrade with corresponding dynamic viscosity 0.02 Newton second divide square meters. The initial after running in process and the final after working at 253 Newton and 553 Newton. Surface roughness of the journal bearing and the shafts was measured by using surface roughness tester in pursuant of DIN 3768. Surface roughness parameters such as center line average, average peak to valley height, and maximum peak to valley height were measured by using a deriving unit at a tracing speed of 0.5 millimeters divide seconds with traversing and cutoff lengths 4.8 millimeters. The unit was connected to the measuring indicator in order to read measured roughness values. The average values of the 5 roughness measurements were taken. Table 1 shown the results of the surface roughness before and after tests. The chemical composition of the alloys and measured molybdenum disulfide particle size range is shown in table 2. The effective bearing length was taken as 18 mm to operate at a pressure of 2.66 megapascal because the maximum allowable load of the test rig was 553 Newton. The diameter of the shaft and thin bolt journal bearing are 760 and 850 millimeter respectively. The bearings had a bearing clearance of 45 micrometer. Physical methods. A schematic representation of the test rig is shown in figure 2. As shown in figure 2, the rig consists of a rigid tubular steel frame equipped with pneumatically operated pressurized oil supply, a direct current solid state variable speed control unit, and then a split journal bearing assembly and instrumentation for indicating speed and armature current. The apparatus operates a 240 voltage single phase electric supply and an air supply at a pressure of none less than 0.6 megapascal. In this test rig, the hydrostatic pad is made of mill steel and accurately lapped to fit the journal bearing housing. 11 jets provided the oil for the hydrostatic lift enabled the load to increase up 553 Newton to be transmitted to the bearing without affecting the sensitivity of friction torque measurement in here. The friction torque was measured by using Watson bridge circuits with strain gauge on the torque plate. The torque signal obtained from the bridge circuit was transmitted to the recorder and this enabled monitoring and recording the signals. After this process, the journal bearings were tested at rotational speed ranging from 0 to 1100 RPM for 5 minutes at each speed. And then the structure of the particles were characterized by scanning electron microscopy, as shown in figure 3. The molybdenum disulfide nanoparticles have a platelet-like shape with an average diameter of 3.2 micrometer. Results and discussions. It's seen in figure 4. As shown in figure 4, using molybdenum disulfide additives, lower friction torque value were obtained in the test compared to the base oil. This difference is even more pronounced in boundary and mixed friction regions. For example, an average increases of 0.3 and 0.6 Newton meter is observed in the friction torque at 253 Newton and 553 Newton bearing loads in the boundary friction region respectively. It is seen that the friction torque values in the bearing increases with the increasing bearing load. As a result, it has been determined that the effect of molybdenum disulfide additives is dominant in the metal-to-metal contact operation conditions than that of the liquid film regions. In the bearing test with different oils performed at 253 Newton bearing load, the transition speed values are very close to each other and are around 14 RPM. It was determined that these differences increased at 553 Newton bed load and was approximately 20 RPM. In the fluid friction region, this difference is approximately 0.02 Newton meter at low load and 0.01 Newton meter at high load. In order to determine the friction coefficient in the plain bearing, firstly the peripheral friction force values in the bearing were measured, and then the friction coefficient values in the bearing were obtained by taking the ratio of this friction force to the bearing load. The effect of different oil on the friction coefficient is given in figure 5. As can be seen in figure 5, higher friction coefficient values were obtained in the base oil test compared to the molybdenum disulfide additive oil. This difference is even more pronounced in the boundary and mixed lubrication regions. It's seen that the friction coefficient values formed in the bearing decrease with the increasing bearing load. The reason for the decrease may be that, compared to the friction force, the increase in the bearing load is higher, or the internal friction of the oil decreases as a result of the thinning of the oil film between the surfaces. As a result, it has been determined that the effect of surface roughness is effective in terms of friction coefficients under metal-to-metal contact operating conditions. Using molybdenum disulfide particles, the effect of oil temperature on the friction torque is given in figure 6. As shown in figure 6, higher friction torque values were obtained at higher oil temperatures in the tests. Compared to the base oil, these tests using oil with molybdenum disulfide additives reveal lower temperature differences. These differences decreasing with the load increasing. In the fluid friction region, the friction torque in the bearing decreases with the increasing oil temperature, while the friction torque decreases due to the increasing temperature. The transient speed increases. With the increases in the temperature in the fluid film friction regions, the friction torque also decreases while the transition speed increases. As a result, it has been determined that the effect of oil temperature is effective in terms of the friction torque under metal-to-metal contact operating conditions. Conclusions. The aim of this to further reduce the friction by adding inorganic compounds as additives to the engine oils used between the shaft and bearings. The results of current study indicates that all the investigated factors like base oil and the additive oil, test pressure, test speed play an important role in controlling the friction behavior of the thin-walled journal bearings. In this study, by adding 1% by weight molybdenum disulfide to the base oil Shell-Tellus 10 engine oil, the effect of molybdenum disulfide additives on the bearing performance were examined and the following results obtained. 1. Compared to the base oil, the molybdenum disulfide additives exhibit less frictional behavior at increasing bearing load and temperatures. 2. Molybdenum disulfide additives is more effective in the mixed friction region than that of liquid film region. These results can be evaluated taking into consideration the forming of turbofilm in boundary or mixed lubrication. 3. The friction reduction effects of molybdenum disulfide additives are increasing with higher bearing loads. 4. As a result of these tests, it is concluded that molybdenum disulfide additives reduces wear and increases general bearing life. My presentation is finished in here. If you have any questions, please don't hesitate to contact me via email. Goodbye.